Welcome to Let's Get to the Marks, going through an A-level chemistry walkthrough pack on carboxylic acids and their derivatives. Okay, this is a physics and maths tutor pack. It's the fourth one in a four-part video series covering the physics and maths tutor, carboxylic acids and their derivatives revision pack for AQA chemistry. Big shout out to the members, Nicola Korzek and Ash Ford. Thanks for supporting the channel. Let's get into this one. Question 8. This question is about making a diester from cyclohexanol. State the type of reaction in step 1. Give the name of the reagent needed for step 1 and the type of reaction and reagent. We've got 2 lines there for putting it. It's worth 2 marks. You can see we've got an alcohol going to an alkene to compound G, then going to a diol, and then down below we've got like a diester. You can see those ester links here and here. So what is the name for the reagent in step 1? Well, we're going from an alcohol to an alkene. So alcohol to alkene, hopefully you know what that is. The type of reaction, that's a dehydration. You can say elimination. Remember, you're removing a water molecule. You're removing that hydroxide group and a hydrogen as well. And that's going to leave us with that double bond. We call that dehydration or elimination. Okay, and the reagent we need is H2SO4, that's sulfuric acid. And that will score you 2 marks for this first question. Don't forget, you might want to grab some scrap paper, a pen, a calculator, pause the video and have a go at the start of each question. Right, state the reagents needed and give the equations for step 2 and 3. So let's check out step 2 and 3. And it does tell us explicitly, show the structure of compound G in your equations. So we need to show the actual structure of that. So let's look at step 2. We're going from this alkene and we end up at a diol, right? So what we're going to need to do in between is become a haloalkene. We're going to do like electrophilic addition or some sort of addition, nucleophilic, whatever. But we're going to do some addition and we're going to end up with a haloalkene. So step 2, my reagent is bromine. You could say chlorine, iodine, or any other sort of halogen. So you know that one from your AS content. Yeah. Now, haloalkanes can also be called halogenoalkanes. It all just depends on what you like. So we're going to add bromine here. It's going to add across the double bond. And we're going to get a dibromo cycloalkane form. Okay, let's look at the next one. So we want to go from that. What happens if you want to replace those with OH groups? That is just straightforward substitution. We can do that using a strong alkali, something like sodium hydroxide or potassium hydroxide. Now we do need to redraw compound G. So we're going to redraw that here. And then we're going to add sodium hydroxide. As I say, you could add lithium hydroxide or potassium hydroxide. And we're going to need 2 sodium hydroxides because we need to replace those bromines with 2 hydroxide groups. So that's a bit of substitution. We're probably going to get sodium bromide formed and you're going to get 2 molecules of that form. My kids are going nuts next door. So if you hear lots of screaming and stuff, there's no axe murderers in the house. It's just my kids trampolining off the sofa. Right, part C, cyclohexane 1,2-diol reacts with ethane diol dichloride. Give the name of the mechanism for this reaction. Complete the mechanism to show the formation of one ester link in the first step of this reaction. Right. This reaction is going to be nucleophilic addition elimination. You probably can get away with just saying addition elimination. Okay, let's zing down and check out the rest of this question. So we've got the mechanism here. Now, funnily enough, if you go onto the mark scheme, I'll put them in the link. If you go onto the mark scheme, they kind of just messed up on the mark scheme here and they didn't have an answer. So that's what I'm going to show you now, how to go through for this. So they want the first part of the mechanism. I'm going to show you the whole addition elimination mechanism. Might as well, eh? Right, so what's going to happen? We're going to look at one hydroxide first just to form one ester link. So we've got the lone pair being donated from the hydroxide group to the carbon. Why? Because it's delta positive. You don't need to show the delta positive in AQA, but the carbon is slightly positive because that's a polar bond. Now the oxygen will temporarily break the double bond in order to allow a bond to form with the hydroxide ion. Otherwise carbon can't have 5 bonds. So I'm going to redraw out what it looks like now. So in order to get the marks for that, you'd need 2 curly arrows and the lone pair on the hydroxide. Now, what we're going to do over here, we're going to redraw it out. We've got a lone pair and a negative sign on the oxygen. So you now have to include the negative sign on the oxygen. We've got the Cl still attached and the COCl at the bottom there. So what's going to happen here? Well, this is an oxonium ion. This oxygen now has 3 bonds around it. So we put a plus sign on that. And we're going to put the lone pair from the oxygen going back to reform the double bond. The chlorine, therefore, cannot be allowed to stay because that would mean carbon has 5 bonds around it. So the chlorine is snapping off to allow the double bond, the carbonyl bond, to reform. So I'm going to redraw it again. Again, there's 2 curly arrows there, a plus sign on the oxygen and a lone pair with a negative on that oxygen. Now we're going to redraw it. I've still got the plus sign on the oxygen. However, the double bond has reformed. The chlorine has buggered off. And I've still got the COCl at the bottom. Now I'm going to put my lone pair chlorine over here, my anion, because it's snapped off. I've circled it in green. Obviously, the way I've drawn it's a bit awkward because it's like crept over there, but never mind. I've still got this bit because we're not showing that form an ester link. That can also form an ester link with the hydroxide group, but the question didn't want that. So now I'm showing the lone pair from the chloride ion attacking the hydrogen on the oxonium. The hydrogen can only form 1 bond, so it's going to join with the HCl. That's what's the elimination part, and it donates its pair of electrons to the positive charge on the oxygen, cancelling that out. Okay, so the reason why we call this bit elimination is because you're going to get hydrogen chloride eliminated. I mean, sometimes when you're dealing with carboxylic acids and you're not dealing with acyl chloride type molecules, you'll get water eliminated. So it'll still be elimination. But this elimination step, the hydrogen chloride gets eliminated. Right. Suggests why chemists usually aim to design production methods with fewer steps with a higher percentage atom economy. So basically, if you have fewer steps, you're going to save energy and you'll increase the yield. Remember, each step in a chemical reaction involves the yield getting less because you're going to leave some powder behind. You're going to get some reactants not fully reacting and all of that kind of stuff. And high percentage atom economy means you probably have less products, and the more useful products, less wasted products. Okay, check out this method for making aspirin. Add 6 grams of salicylic acid to a weighing boat. Place the weighing boat on a 2 decimal place balance and record the mass. Tip the salicylic acid into a 100 centimeter cube conical flask. Step 4 is missing. We're going to be asked about that. Add 10 centimeter cubes of ethanoic anhydride and to the conical flask and swirl. You can pause the video and read through that if you really fancy it. Right, A, describe the instruction that is missing from step 4 of the method. Why is this step necessary? So what should have happened after you weigh something? Can you tip it into a flask? What should you do next? You should re-weigh the weighing boat or the crucible or whatever you've been weighing in. You need to re-weigh it so that you can get an accurate calculation of the amount of mass you've actually added. You might have weighed out 6 grams, but by the time you tip it in, maybe only 5.98 go into the flask. And that's because you'll leave like 0.02 or whatever, 0.002 or whatever will be left behind. You're going to leave a little bit left behind in the weighing boat. So suggest a suitable apparatus for measuring out 10 centimeter cubed of a liquid. So I would use a 10 centimeter cube pipette. Obviously, if it was 2 centimeter, you're not going to get a 2 centimeter cube pipette. But you could use a measuring cylinder. You could use a burette. There's other ways you could do it. I always like the pipette because each pipette only measures a set amount. So you definitely can't make any mistakes with that. Identify a hazard with concentrated phosphoric acid. It's corrosive, so that thing is going to burn up your skin. So yeah, that's the hazard. Right, D, complete the equation for the reaction of salicylic acid with ethanoic anhydride to produce aspirin. It's 1 mark. Basically, what they're getting you to do here is work out the formula for ethanoic anhydride, the structural formula, where you show the brackets and you show how everything's joined together. You can write the displayed formula in order to help you write the structural formula. So ethanoic anhydride. So you're looking at like 2 carboxylic acids, 2 ethanoic acids joined together. With that oxygen linking them in the middle. So what we want to do here, I'm going to draw out the structure of ethanoic anhydride. So we've got a methyl group, we've got the carbonyl bond, then we come down to an O. So it's like a carboxylic acid that's had another carboxylic acid added to it in place of the hydrogen atom there. So there we go. With an elimination of water, obviously, you join these 2 carboxylic acids together, and this would be their formula, CH3CO times 2, and then you've got the little O that joins them in the middle. That is on the side on its own, and that will get you that mark. Okay, moving on. E, we have an amount of substance question. 6.01 grams of salicylic acid, Mr138, is reacted with 10.5 centimeter cubed of ethanoic acid anhydride, Mr102. Reaction yield is 84.1. Density is 1.08 gram per centimeter cubed for ethanoic anhydride. Show by calculation which reagent is in excess. So I know straight away I'm going to need mass over MR times mole. So even if you ain't got a clue where to start, look, straight away I would start here. Look, I've been given 6.01 grams and I've been given the MR. Bang, I can work out the moles of the salicylic acid. Just make sure you label it on the paper so you don't forget as you're scribbling all over the paper with your answers, you don't forget. So the examiner is going to come through and hand you out marks for all these calculations you do. So just make sure you label them so you know what you're talking about. So now, my answer might differ slightly from the mark scheme because I might do some rounding, like this is 0.04355. I probably should just leave that in the calculator, but for speed, I'm round, so my answer might not be 100% correct, but the method is. But you just might need to leave it all in your scientific calculator. So there's my salicylic acid moles. The next thing I want to do is work out ethanoic anhydride moles. Now, they haven't given me the grams of ethanoic anhydride. I'm going to have to work that out from its density. So I've been told I've got 10.5 centimeter cube, that's volume, and if I do volume times density, I'm going to get the grams, I'm going to get the mass, and then I can use the MR to work out the moles. So have a go at that. So I'm going to do 1.08 for the density times 10.5 for the volume. So density times volume gives me mass, and that should be 11.34 grams. Now that I've got the grams of ethanoic anhydride, what we can do with that, I can divide that by the MR and that will give me the moles, right? So I'm going to divide it by, oh my days, I can't even write out a number, 102. So I'm going to divide it by 102, which is the MR of ethanoic anhydride, and that's going to give me the moles of ethanoic anhydride. And I've got 0.111111, whatever, 8 moles. Okay, now, do I have to put all it like that? Well, again, you could do some rounding and whatnot. So just check. You should leave it all in your scientific calculator, but I'm breaking it all down because I'm doing it step by step. Okay, that way your answer will be more accurate if you don't keep. Oh my gosh, I can't spell ethanoic acid. Oh no, ethanoic anhydride. That should say ethanoic, by the way. That's just my crusty spelling. I'm not going to go back and change that. So which is in excess? Is it the salicylic acid or the ethanoic anhydride? They're both in a 1-to-1 ratio, so we just need to look which one is bigger. And the answer is the ethanoic acid, 0.111 moles, is bigger than 0.0436 moles, right? So the ethanoic acid is in excess. We can even work out if we want and show the examiner, ooh, I can tell you how many moles would be left over. So 0.0675 moles of ethanoic acid is in excess. It's left over that many moles. If you want, you could work it out with the grams by times it by MR and say how many grams are left over, but we're not going to do that. So ethanoic anhydride is the reagent in excess. Now what I need to do is work out, the next part of this question was to work out the grams of aspirin that are produced. So I'm going to use, they've given us yield, so we need to use the yield calculation. So yield, percentage yield, is the actual mass over the maximum mass times 100. So we need to find the actual mass, and so we need to work out the maximum mass, and then we can do it. So we know the MR is 180, and I know the moles of aspirin. If everything went perfect, I have to look at the limiting reagent to how much aspirin I could make. I can't look at the excess reagent because that's going to have leftover moles that are unreacted. So I look at the limiting reactant, and that is salicylic acid. 0.0436 moles of aspirin is the max I can make because that's the max amount of salicylic acid we have. It's a 1-to-1 reaction. So I'm going to do 0.0436 times 180, and this is going to give me the maximum grams of aspirin I can make, and it's 7.848 grams, not moles. I put N, choose Louise. Right, bear in mind that I probably could have used 0.04355, which was in my scientific calculator, but I couldn't be bothered to write all those numbers down. So now I'm going to do 84. I'm going to set this out as an equation. Now that should be grams, by the way. Let's just change that so we don't get too confused. 7.848 grams, whatever. I should really round that to 7.85. I'm getting super sloppy today, peeps. Okay. So X is my unknown actual mass. what do I need to do? Well, I've got times 100 there. Divide both sides of the equal sign by 100, and I'll end up with 0.841 times 7.84. And that is going to give me X. So I end up with 6.60 grams. Now, it might be like 6.58 on the mark scheme or whatever, but, the method's all correct here. So boom, well done. Right, let's move on and finish this pack of carboxylic acids. I'll be glad to get this one out of the way. I started this one about a year ago and just haven't got around to finishing it off. Okay, zing down. F suggests two ways in which the melting point of crude aspirin collected in step 9 would differ from the melting point of pure aspirin. Right, crude is a mixture, right? Remember, crude oil is a mixture. Crude means there's other bits inside there. So it's a mixture. How do mixtures differ than pure substances? So they differ with their melting points. The crude substance will probably have a lower melting point, but also it's going to melt over a range. A crude substance or a mixture will melt over a range. So if its melting point was 78, it might start melting at 76 and not stop melting until 82. So it has a range, whereas a pure substance will melt at an exact melting point. Right, crude aspirin can be purified by recrystallization using hot ethanol. Boiling point 78 degrees is the solvent, so ethanol's boiling point is 78. Describe two important precautions when heating the mixture of ethanol and crude aspirin. Right, well, think about ethanol. What do you know about it? It's an alcohol. They're flammable. They're used in fuels. I mean, they use ethanol or they use alcohol in cars, in combustion engines in Brazil. So use an electric heater. Don't use a naked Bunsen burner flame. That's what we call flames, and because it might set fire to the ethanol. And also keep the boiling point below 78 degrees. If you keep the boiling point above 78 degrees, then the ethanol, which is a solvent, will evaporate and you'll lose your solvent. So keep the boiling point below the boiling point of ethanol, so below 78, and use an electric heater, not a naked Bunsen burner flame. Right. H. The pure aspirin is filtered under reduced pressure. A small amount of cold ethanol is then poured through the Buchner funnel. Explain the purpose of adding a small amount of cold ethanol. Now, there's 2 points there. The fact that they've said small amount could get you a mark, and the fact that they've said cold ethanol could get you a mark. So, we want to use cold ethanol because it will remove soluble impurities, and we want to use a small amount because we don't want to dissolve any of our aspirin and dissolve any of that and run that off and lose that when we filter. Also, not insoluble, soluble impurities. Also, we want it to be cold because, again, if it's hot, we're more likely to dissolve some of the aspirin, which we don't want to redissolve any of the aspirin, which will dissolve in the hot solvent. So we cool it so we don't dissolve the aspirin. And yeah, if it's hot, it will increase the amount of stuff that can dissolve in it, which is not what we want. All right, where are we? Last part to the pack. A sample of crude aspirin is kept to compare with purified aspirin. Describe one difference in appearance. Right, if you have something that's a mixture, you're going to get so aspirin is white. Pure aspirin will be white. A mixture will be an off-white color. Why? Because there's more than one thing in it. So if you mix different paints together, you're going to get like a mixed color. But if it's pure, you're just going to get something made of one clear color. It'll be shinier. It'll have larger crystals, more pointy, sharper crystals. Not all different all sizes of crystals. So if it's a mixture, you're going to get a mixture of shapes, sizes, colors. Okay, last question, question 10. Which of these involves addition, elimination? So when we look at this, we can just look at these and quickly work out the mechanisms. So what have I got here? I've got double bond forming. That means I've got elimination or dehydration, but there's no addition going on here. It's just straight up bang elimination. And then for C, I'm looking at C now. C's a double bond I'm seeing with chlorine adding across the double bond. That's a straight up addition. There's no elimination there. And then I'm looking at this final one. I've got the bromine atom. This is a haloalkane or halogenoalkane becoming an alcohol. That's substitution. So we've got like nucleophilic substitution going on down there. So that's definitely not it. So the answer's B. And we've already done this mechanism quite a few times. We've done this type of mechanism. quite a few times, but just to show you again, I'm not going to do the whole mechanism, but just to show you again, we've got the addition section of this where the lone pair on the oxygen is going to go to the carbon because it's a polar bond. The carbon's delta positive. The carbon's going to temporarily, the carbonyl bond is going to break. That's the addition section. We've got nothing being eliminated there. And then the next two parts of this reaction involve elimination, and we're going to have the hydrogen chloride molecule eliminated. So first of all, we've got addition and then elimination. Oh my God, I can't even speak properly. So yeah, I'm not going to do the rest of this, but yeah, you get the coup. Yeah, whatever. Right. I should have a chlorine atom coming off there. Never mind. Okay, skip all of that. What I'm going to say, guys, you know what I'm going to say. Yeah, ignore this molecule I've drawn here. Ignore this bit, but you get the idea. Awesome, awesome, awesome. Whiffle, waffle, waffle. Enough of that, Tom. Make sure, guys, sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. I'll see you guys in the next video.
You're still here? It's over.